Hey guys, welcome to day 2 of VSEPR. All right, so before this lecture, you guys participated in a inquiry investigation in a sense, right? To clarify some stuff about VSEPR, shapes of molecules, just to make sure that you have in your brain solidified the types of shapes that our molecules can take in real life. All right. What we're going to do today is we're going to start looking at polarity. And in order to talk about polarity, I have a couple images on my screen, right? I have a butterfly, I have a tennis racket, okay, or a badminton racket, okay, and I have a hand. And you see that there are dotted lines drawn down each of them, right? And if you guys have ever taken an art class before, you guys know that these dotted lines symbolize lines of symmetry, right? Because if I folded my butterfly across the dotted line here, right, it's going to be symmetrical. It's the same on each side, right? Same with this racket here, okay? With the hand, right, no matter how I cut it, right, it's never going to be symmetrical, right? And so when we're talking about our molecules and we are talking about polarity, okay, we're actually talking about symmetry. All right, so what we're going to be able to do today, this is our objective. You guys can copy it down in your notes. You're going to be able to predict the polarity of an overall molecule given its shape. Okay, and you're even going to be able to do it given its formula, but we're just going to focus on shape itself. All right, so we have learned that within the molecule itself, we have a nonpolar covalent bond and we have a polar covalent bond. So this is going back to last week, okay, when we talked about polar versus nonpolar, right? We know that a nonpolar covalent bond, my electrons are shared equally, okay? There's no electronegativity difference. And in a polar covalent bond, electrons are shared unequally. So I have a large electronegative difference between my two elements, and it makes the bonds themselves polar and nonpolar. Okay? So within the molecule, I can have polar and nonpolar. Okay? However, just like within the bonds, my molecule as a whole can also be polar and nonpolar. And this is going to relate to symmetry. Okay? You see here, right, we have a symmetric drawing versus an asymmetric drawing. And so this is what's going to be able to tell me if my overall molecule and not just my bonds are polar versus nonpolar. Okay, so let's look at an example here. Okay. I have nonpolar molecules, meaning my molecule itself is symmetrical along the central atom, right? So on each side, okay, for each bond of my central atom, it is the same, okay? So within the molecule itself, okay, I have C bonded to O on each side, right? So within the molecule, C has an electronegativity of 2.5. O has an electronegativity of 3.5, and my difference between the two is 1.0. So my O and my C itself, okay, right, is a polar bond. So this here is a polar bond. This here is a polar bond. However, because I am symmetrical around C, my molecule itself is non-polar. So I have polar bonds within the molecule, but my molecule itself is non-polar because each side can cancel each other out. Okay. In order to be non-polar as a molecule itself, right? Remember, we're talking about the molecule overall, not just the bonds, okay? I need to have at least two elements with the same electronegativity at each end if I'm talking about linear, okay? Or I need to have surrounding molecules that are all the same, okay, right? So in this case, you see I have a trigonal planar that has molecules that are all the same surrounding B, boron. You see around C here, I have molecules that are all the same. I have F, okay? So I have polar and nonpolar, right? But anytime that I have something that is the same element surrounding my entire central atom, okay, it's going to be nonpolar, right? Polar molecules, on the other hand, okay, are going to be molecules that are not symmetrical, right? If I cut this element in half, or this molecule in half along my central atom, H and N are not the same, so I'm no longer symmetrical, okay? Within the molecule itself, I have both polar and nonpolar bonds, right? These are all my electronegativities, right? My difference here is a 0.4 versus a 0.5, so I have polar and nonpolar bonds within my molecule itself, okay? However, the molecule itself is going to be not symmetrical, so I have a polar molecule. So notice how we're looking at within the molecule, or within the molecule itself versus the molecule as a whole, okay? On your exam, you will be having to differentiate between the bonds themselves, right, if it's polar or nonpolar covalent, and also the molecule overall, so if the molecule is polar and nonpolar, okay? So reading the question is very important, okay? If I have a polar molecule, okay, my surrounding molecules are going to be different, okay? Meaning, if I looked at a trigonal planar, right, they're not all H's, they're not all O's, okay? So I now have this unsymmetrical or asymmetrical distribution, okay? Another thing to keep in mind, that anytime I have lone pairs, okay, so trigonal, pyramidal, right, my pyramidal and my bent shapes, okay, anytime I have lone pairs, I am also automatically polar, okay, because I have these lone pairs present. So anytime I have lone pairs, polar. Anytime I have unequal, okay, surrounding atoms, it's also polar, okay. The reason why it's important to know if it's polar or nonpolar as a molecule as itself is it actually helps us determine some of our chemical reactions that are going to occur, okay? If you guys have heard of like dissolve like before, okay, it talks about how similar elements and molecules can dissolve certain elements and molecules, right? And this is all based on the polarity of my molecules themselves, okay? Polar molecules are only going to be able to dissolve other polar molecules, okay? Nonpolar molecules are only going to be able to dissolve nonpolar molecules, okay? And so this plays a huge role in when we're talking about solubility, okay? And solubility is the dissolving of something, okay? Right? So if I think about oil and water, and you guys have probably done this before, okay? When I think about oil and water, right, oil and water do not dissolve in one another, right? The oil kind of sits on top of the water. It doesn't mix. The reasoning why, right, is water is a polar molecule, my H2O, right? I have a bunch of polar molecules, okay? Oil is a non-polar molecule, meaning it has that surrounding, that equal symmetrical surrounding, right? So when I add polar and nonpolar together, they can't dissolve in one another, right? So the shapes of molecules, okay, helps determine our polarity of our molecules, which helps determine if a reaction or a mixture can even happen, okay? Okay, so like dissolve likes is why we need to know this, okay? So, super short video coming to an end. Please write your summary to answer the following question. How can the shape predict the polarity? Okay, here's some examples, maybe. Okay, once you're done with that, we're going to do some practice stuff. Okay, I'll have the solution or the answer key up at solution station. Okay. And then tomorrow we will do our last day of Unit 3 to prep for your test. All right. If you guys have questions, let me know. I'm going to come around and field some stuff. Okay.